All right, so I submitted a lightning talk. And this is something that came out of the work you just heard about with XDP queuing, because when we were implementing the kernel bits for this, this fell out of it. I'll talk about it. So first, what is XDP? How does it work? I'm not going to bore you with that. I hope you paid attention. Otherwise, this is actually the real flowchart that we follow in XDP land. So BPF proc test run. How many of you have heard of BPF proc test run? Jesper has heard of it. Great, and a few others. Awesome. So this is the BPF subsystem in the kernel. Works by multiplexing a few dozen different commands through the BPF syscall, and one of them is this BPF proc test run, which now also just calls BPF proc run as an alias. And what it does is you can supply a file descriptor for a BPF program that you loaded into the kernel previously, and you can supply it with data in and data out, which is just a buffer of packet data, and you can supply it with a context object from user space. Then you can set a repeat number of repetitions you want to run, and then the kernel will take this program and it will run it for you, and you will get the result back out. And this is used, like you can use this for unit testing your XDP program, for example. Like you build a packet in a data buffer in user space, you pass it into the kernel, it will execute your XDP program, and you can see that it did the right modifications. You can even see you get the return code back out, so you can see, okay, this packet was redirected like I wanted to. So like the self-test uses this, and you can just use it for unit testing your own thing. The problem with this is that it doesn't do anything other than execute your program and give your result back out. So if you say your XDP program returns XDP redirect to send the packet somewhere, the kernel will just send the return value back out to user space and say, this program redirected, and then nothing more happens. So we introduced this flag because one of the things that the work Frey is doing with packet queuing is that we want to actually test these PIFO maps that store packets. So we want to be able to redirect an XDP frame into a PIFO map, and then we want to afterwards see, okay, this actually turned out in the PIFO map and it works and so on. And I thought, when I was implementing this first, like, oh, we can just use proc test run, that's great, we can check it this way. And then I ran into this thing where it doesn't actually do anything. So we added a feature where we have a new flag that you can supply to proc test run. And what it does is that instead of returning the packet to user space, it will act on it. So you can no longer supply a data out or a context out object when you use this flag because there's no output. Instead, the kernel will just pretend that the packet you just executed in the syscall actually came in on an interface, and it will do whatever it was going to do with it. So if you return XDP pass, you will get packet injection as if that packet arrived on the interface. So you supply the interface by putting it into the context object that you supply to the kernel. Or you can XDP redirect or XDP TX, and then it will go out an interface. So this, like, we translate XDP TX into an XDP redirect, so it goes out because the real XDP TX is something that only happens in the driver. We can't like immediately DMA the packet back out. So we just turn it into an NDO XDP XMET. And then we do a lot of optimizations for batching, as we do usually in XDP. So there's a new command on this struct that I didn't include here, which is now called the batch size, which, when you run it, the kernel will allocate a number of patches equal to the batch size, which is 64 by default, and then it will initialize all these pages with the data you supplied from user space, and then it'll keep looping and recycle these pages. So this means that if your XDP program modifies the packet and redirects it out an interface, and then that page gets recycled, then the next time your XDP program runs, it will get the pre-modified packet already. So you have to sort of be able to handle this, but that means it goes really fast. And this means you can run stuff. And the nice thing about this feature is that as one of the only features in the BPF subsystem, it came with documentation when we introduced that. So what can we do with this? We can inject packets into the kernel with XDP pass, like tests that you can just gain any packet from on the interface. And you can test the XDP redirect infrastructure, which was the original reason for creating this feature. And then you can send packets. So we can build a traffic generator, which is what I did. And I'm going to attempt a live demo of this. I was sacrificing goats to the demo gods while the others were talking, as you can see. So this is an SSH session into my testbed, and we're going to try to run. You just supply XDP traffic gen. This tool is going to be soon part of the XDP tools project. And you just go, I would like to send UDP packets out of this interface. You can supply like destination addresses and so on, but we don't care. We're just going to drop them otherwise. And then it just starts running. And this is the number to look at. 8.8 million packets per second. These are 64-byte packets. This is on a single core. So what happens if we say 6 cores? This is a 6-core machine. Now we get 117 million packets per second of 64-byte packets. And for each of these, we introduce we run an XDP program so you can modify. This is the fast one. It doesn't do anything. It just transmits packets as fast as it can. But you can do modifications. So say we want to spray these packets over 100 different UDP ports when we send them. Then it goes a bit slower, but still pretty good. And then the fun thing becomes, so this is all UDP. Can we do TCP? Yes, we can. So I'll have a slide explaining how this works, but the nice thing to notice is this. This is a terrible TCP implementation. So I reused the XDP TX statistics just because it was a convenient way of getting data out. So this is the actual bandwidth used on the wire, and this is how much of that is retransmits. Congestion control is there for a reason. Yeah, so that's the XDP traffic generator using this. This is some of the same-ish results in case the demo didn't work. So what does this actually do? It prepares a packet buffer in the user space, like builds a packet struct, computes checksum and so on, and passes it into BPF test run with a really large number for the repeat parameters. It'll spin in the kernel a lot of times. And then this is the simple one that did 117 million packets. It just does a BPF redirect, doesn't even touch the packet data. So in general, in XDP, as soon as you actually look at the contents of the packet, your performance will drop by like 10-20%. Because now you have to take sometimes a cache miss, but at least you'll start touching more data. And then the dynamic port that was a bit slower, that has a bigger program that will look at the packet data, update the UDP port to the next one in a sequence, and just keep a counter for every iteration of the program, and then redirect it. So yes, as you saw, we can do TCP. What this does is you set up the connection from user space because we don't want to deal with all the handshake stuff that TCP does. That's very complicated. And then we install a TCP program on the physical interface so that when the kernel sends out the handshake for the TCP, we intercept the reply, and then we can pull out all the sequence numbers so we know where to start in the sequence the next time. And then once we've gotten the handshake set up, the HTTP program starts taking over. So any additional acts that come in, we will process and then drop them. So from the point of the view of our local stack, this flow is now, doesn't see this anymore, but then we can just start spewing out XDP TCP packets. And then we just send out packets as much as we can in sequence, and then when we run out against the right edge of the C-wind, we just start dropping packets. So you see this is a totally different example with, for some reason I was getting 10 more gigabits per second the last time I ran this than the live demo now. But some of them are drops. That's when we run out against the window. And what it does to handle return, the reason for this is that the way I'm handling retransmits is when you get a do back, you just rewind the window all the way back to the last act you got and start spraying out the whole window again. And as you can imagine, this is a bit inefficient. But in principle, it's fun to play with. I have some plans to try to make it a bit smarter and see. But the TCP program runs on a single core, by the way. So yeah. It's a nice way to DOS your TCP stack. Yeah, questions? Why not try playing with this for yourself? What else could we do with it? It'll be fun. And like questions to anything related to XDP, I guess, if anyone has thought about something to ask Jesper while we were talking, or Frey. Yes?
So for someone who's not familiar with XDP, can you elaborate a little bit on the difference between XDP-TX and XDP redirect?
Yes, so normally when XDP runs in the driver will execute a BPF program as the first thing that happens when the packet comes in from DNA. And then it will act on the return code of the XDP program. And XDP-TX means send the packet back out the same interface immediately. And because normally the XDP program is run inside the driver can immediately act on this and just do a DMA transfer back out the other way. Whereas XDP redirect is you supply an argument to this saying, I want to redirect to this other IF index. And so what the kernel does when you do this is it will actually behind the scenes, it will buffer up to 16 packets to do batching. So it will sort of save the packet, and then once the mapping cycle in the driver is done, it will take all these packets that is saved, and it will call another NDO in the other driver, because that might be a completely different interface. You can even redirect into a VF, and then transmit those frames out. So it's sort of an implementation detail of two different ways. Not all drivers implement XDP redirect, because that's a separate driver NDO compared to just TX. When you're already doing XDP, you can just send them back out. So XDP TX, for example, the Facebook Katran with load balancer works by XDP. So you can do happening, right? It comes in and you rewrite the packet and you send it back out and it goes somewhere else. That's what the main use case of XDP TX.
And the driver has to support XDP redirect for your traffic generator.
Yeah, so and the nice thing about XDP redirect is actually two things to support. Like one thing is supporting XDP redirect on ingress, like the driver understands the return code and can send it to another driver. And then implementing the NDO XDP X mode means I can be the target of a redirect. And you can only use this with drivers that has the NDO XDP X.
Okay, thanks.
And like the only way to figure out which drivers that is grabbing for NDO XDP X in the software, unfortunately.
Is there anything other than network that is little use? Or audio interface or?
I saw a patch series someone's trying to do BPF for the HIT subsystem. But that's, I've heard about people wanting to do it for storage, but I don't think anyone has really done it.
Have you had multiple presentations of this?
What?
Something,
yeah.
I don't think there's any.
But for in the mainline, we only have this for networking. Like BPF, you can use BPF for tracing. That's sort of the all main use case. You can attach a BPF program as a K-probe to any function in the kernel, and it'll get the arguments every time that function is run, and you can put that out to user space and do statistics and all this stuff. And there's a bunch of, like, few dozen BPF hooks that does different things in the kernel. So people build like whole data planes with cloud stuff on it, and you do observability. It's sort of about, if you've heard of dtrace from Solaris, it's sort of on par with that in terms of what you can do for tracing. If you look at the BPF trace utility, that has a lot of nice one-liners where you can say, get a histogram of every PID that does a certain syscall in the system, or all kinds of stuff.
The big thing is security.
Yeah. Oh yeah, that's
for security hooks. Like you will have BPF program implementing the security policy you want.
Yeah, so there's a BPF LSM, which executes a BPF program in every LSM hook in the kernel.
Now it's such, I feel like fair enough again. You just sprinkle it everywhere and see what happens.
Yes, and so I wrote a BPF LSM hook that disables BPF.
just as a proof of point. It's like recursion.
Yes. All right. Any more questions?
But I think you should explain that thing with the elf header, which actually strips out the parts that doesn't apply. It's almost like Vulkan, where you have the source code.
Yes. So one of the nice things about BPF in general, and Jesper was alluding to it a little bit with the BTF. So with BPF, we have the type information. So the kernel is now typed self-describing. Every struct in the kernel is a description of this. It is embedded in the kernel image in a binary format. Almost every distro does this now. And then when you write BPF code and load it into the kernel, you can at load time, the libbpf library will inspect this type information and match it to the BPF code that you wrote, which also has type information. It goes like, okay, you want the struct skbuff, and you want this member from that, so I will sort of redirect this. And you can also do checks, so say, does this struct exist in the kernel? Then I want to pass it. And then at load time, libbpf will look at your code and say, okay, if you want to access this struct in the kernel, and it will ask the kernel, do you have this struct? And if it doesn't, it will rewrite like you have an if sentence in the code that says, if this struct field exists, and at load time, libbpf will rewrite that if statement, so it just becomes if 0. And then when you load the BPF program into the kernel, there's a verifier in the kernel which says, oh, this branch is always 0, so I'm going to remove all the code. So you can actually, it does that code elimination for you at load time, which means you can write all this elaborate code that handles all the different kernel versions transparently, and at load time it will magically just remove the parts of the code that you're not using, so you don't pay any runtime cost for it. Which is pretty neat. Yes?
Sorry, this is not related to your talk, but I want to go back to what Jesper mentioned before, this code read, this compile once, run everywhere.
Yeah.
So this DTF is pretty cool because we work with embedded targets, and if you want to use something like DTF trace or these BCC tools, you have this whole LLVM dependency on the target, which is it's not practical. So it's been a year or two since I sort of checked in on this. What's the state of the art? Can I now run these tracing tools on my embedded target, like build a DTF program and
no. So
how far away are we from?
Yes. So BPF trace has its own sort of language that can express BPF, and that will compile a BPF program on the fly, and that still requires an LLVM. But you can write tools yourself using BPF and C code and using this core thing, that the mechanism I just described, where you say, I want to access these parts of the kernel struct, and libbpf will do that, and you don't have to recompile them. So the BCC utility, which is a different tracing utility that uses BPF, has all these Python scripts that does various things. That's also dynamic compiled, but there's an effort to rewrite these in binary, which is now called, I think, it's mostly packaged as libbpf tools, and that is re-implementations of the dynamic Python scripts in C using Core, so you can run them without having a compiler on the system. And you can do this with your own programs as well. So if you write BPF code in C, then you can create utilities that will run on all the different kernel versions without having to recompile them. But BPF trace itself still does dynamic code generation, and I don't think that's likely to change.
Okay, but the libbpf trace, you said?
Libbpf tools is
it's part of the BCC tools.
Okay.
Yeah.
And we have the same request from some of our customers. Banks that apparently don't like to have a compiler on it.
Yeah.
Okay, but the kernel support is all there already.
Yes, and the user space support in libbpf is that. So you just need a kernel that has BTF enabled, which is all the distro kernels, and you compile it yourself. It's just I think it adds a little bit to the kernel image. For a full distro kernel, it adds like a couple of megabytes, and then you have debug information for the whole kernel. And there's some. I think the only exception that it doesn't include right now is per-CPU variables, and there's some efforts to add that. But like for most of the tracing stuff, that's fine. Yes.
What about having your own hooks in a kernel module?
You can do that now. You can do that now. Kernel modules can export functions to BPF. So not hooks, but functions.
That's also some of the work I've been waiting for XDP.
Yeah.
We couldn't do it before. I wanted to have the module to be able to express.
You can call functions.
Yes.
Yeah, so like for tracing, you can attach to module functions already, like that has been the case all the time. And modules will also include BTF type information now. What has like having a hook point, which is like somewhere where the kernel, like for XDP, will call a BPF program and we will act on the result of that BPF program, is not possible for hooks. But what we have now is this thing called kfuncs, which is like BPF helpers. So the kernel exposes a lot of helpers to BPF programs that you can call. And kfuncs is a dynamic way to do that. This using BTF. So it will, and modules can do this. So there's the first use case for this is there's now a contract helper, so that from XDP you can call into contract, pass the packet, send the tuple into contract and see if they're contract entry. And this is exported from the module via this kfunc dynamic helper thing. And that, I think that's 517 or 518. Yes?
For running the hash tool, usually you need all the symbols from the kernel, and it's quite a bit, and you need to get it in sync with everything. Do you know if there's any effort for using BDF?
I think there's, yes. That was, I forget who it was, but I saw something on the mailing list where someone wanted to add enough information that you can do that sort of thing using BDF. It might be something that's not on by default, but I think what they've, so one of the things is having all the names, like the symbol names, which take up a bit of space, but I think what they were discussing is building a special kernel module which contains all the stuff that's not on there by default, and then when you load that, you have all the debugging information, and that would be a few dozen megabytes extra, so it's not sort of something that's loaded into the kernel by default, but it should be available in the system. And I think this is work in progress. You can find it in the lists. Yes?
Just want to mention something about the BPF and LSM in security context with this web environment.
Yeah, so there's an LSM called BPF, which is from the LSM point of view. It's LSM that just executes BPF code. And so what it does is it generates a BPF hook for every LSM hook in the kernel, so that you can write BPF code that will execute and do whatever the LSM system does. And so you just pick which hooks do you want to hook into, and that's your BPF program will be executed, and you can do the same return codes as an LSM module would do. And that's like, I wrote a small example that will attach to the BPF LSM hook a BPF program, which will deny everything, and that's how it disables itself. Yes?
Just out of curiosity, so if the BPF program now can call certain kernel functions, and then further down the whole stack, like the dump stack, will I see the BPF call it
Yes.
in dump stack as well?
Yes.
And how does that look?
It does BPF proc some hex value.
Okay.
You can also see them in perf. Huh?
Has the tag, right?
Yeah, so basically the kernel will hash the bytecode when you load it into the kernel and turn that into a like opaque hash tag that you can also pull out from user space with BPF tool, and that is used in the backtrace system.
And the perf tool today we go in and analyze and get what instruction. There's the digit as 6 instructions, each instruction is the most time.
And you can also attach a BPF tracing program to another BPF program and see what it's doing. It's totals all the way down. All right. Anything more? All right, and we are actually on time.